Okay, so this was one of the questions that was in the booklet that I gave you guys in class that we didn't actually get to do in class. So this was example 14. It comes from a 2015 HSC paper. So the question gives us this scenario where we have water flowing out of a rock pool. And they give us the rate of change of volume with this equation here. The rate of change of volume over time is equal to AT sine 0.5 t. Now, even before we start this question, let's think about what this graph will look like. So what this is telling me is that the rate of change can be graphed using a sine function. Now, sine functions, if you remember, it does this shape and it continues over and over again. That looks a little bit off, but we're going to have to work with it. Now, the thing that's different about our sine function here is that they've actually changed the period or how long it takes to do one full cycle from here all the way down to here. So we've times that by 0.5. And what this means is we shifted it and it now takes longer to do one period. Usually, one period. So usually, this is 2 pi radians. But because we've multiplied it by 0.5, this will actually take us twice as long. So instead of this value at the end, so I'm going to draw that over here, this dot here, instead of that being 2 pi, instead it's 4 pi. In the middle here, instead of it being pi, it's 2 pi. And the vertical points here, that is at pi, and we've got 3 pi here. So we've got a sine function here, and that shows me the rate of change. That's the rate of change of the volume, and shows that at the beginning, it starts positive, so it's increasing, and it's still increasing up until this point. Just remember, when this function is positive, so it's the rate of change over time. When the rate of change is positive, the volume is increasing. So between, let me draw it here, between these points here, it's increasing. And when it's negative, between here to here, it's decreasing. So it's increasing from 0 to 2 pi, and it's decreasing between 2 pi to 4 pi. So let's have a look at the questions. Actually, we've got another piece of information. They also tell us when time is equal to 0, the volume of water is 1,200 liters, and it's increasing. So when time is equal to 0, it's actually going up, and it's increasing. So, part I, the first part of this question. At what time does the volume of water first start to decrease? Now, we've already had a look at this. We've already started thinking about this, and we know that it's the volume of water in the rock pool is decreasing between 2 pi and 4 pi. So we know that we actually need to show this fact. We know that for a sine function, a normal sine function, so sine theta in a normal function, what we said earlier was it's sine theta is negative, for 2 pi when it's not actually 2 pi. It's between pi, theta is between pi and 4 pi. Now, we actually need a sentence before this. I skipped that sentence, my bad. We know the volume is decreasing when the rate of change is negative. So the volume is decreasing when dV on dt is less than 0. So we need to show that 80 sine 0.5 t is less than 0. This is where we use this fact here. Sine theta is negative when theta is between pi and 2 pi. Why? My goodness, making so many mistakes. Apologies, year 12s. I'm going to move this up so we can condense a bit of space. So we know that this fact, so we can just go, so therefore pi less than 0.5t is less than 2.2 pi. This 0.5, when I divide it to both sides, it just times everything by 2. So I've got 2 pi less than t less than 4 pi. So we know that between the times of 2 pi and 4 pi, the volume is decreasing. So the question doesn't ask us what times the volume decrease, but it only asks us when it first starts to decrease. So the first time, this number on the left-hand side is a smaller number, smallest number in this set of values. Therefore, t is equal to 2 pi is the answer that we're looking for. So here what we had to look at was we identified what the graph of the rate of change looked like. We then had to identify that, well, the volume is decreasing when the rate of change is less than 0. And then we solved for that condition. So we solved for that. And notice that sine theta is negative between those two values. And we got the earliest time possible. So those were the few steps that we had to do in order to find the answer for this question. So that's part 1. Okay, let's have a look at part 2. Now in part 2, we want to find the volume of water when t is equal to 3. Volume of water when t is equal to 3. Now, just remember, this equation that we have here, this one in the box that I'm putting here, that only gives me the rate of change. It doesn't actually tell me what the volume is like at any given point. So what we need to do is we need to find an equation that gives me the volume at any given time. And so this is when I differentiated the v, or the volume, with respect to time. So what I need to do is I need to integrate that equation. So 85t, write that properly, with respect to time. Now, just remember, recall, when I integrate a sine function, and there's a linear function inside, just notice here it's a linear function. The power of t is to the power 1. When I integrate this, this will give me negative cos ax plus b times 1 over a plus c for a constant. I'll rewrite that as negative 1 on a cos ax plus b plus c. So when I apply the same rule to this function, the 80 stays the same. So I've got 80 times negative. When I have 1 over 0.5, that gives me 2 5t plus c for some constant c. So it gives me negative 160 cos 0.5t plus c. Now, so we have an equation for that represents the volume of water in the rock pool at any given time t. Now, there's a problem with this. We have this constant at the end here still. So we need to actually figure out what the value of that constant is. Now, if we have a look at the conditions of this question, we know that when time is equal to 0, the volume of water is actually 1,200 liters. So what we can do is we can use that and go, well, we can sub t is equal to 0, v is equal to 1,200. So I'm going to do that. I'm going to go 1,200 is equal to negative 160. Cos of 0, just remember, is 1. If you would like to just draw a cos graph, the cos graph looks like this. It starts at a high point, it goes to a low point, and goes back up to the high point. So this is just 1. So that's negative 160 plus c. So when I rearrange that gives me c is equal to 1,360. So we've got a formula which represents the volume at any given point. And it's this little formula here. Cool. So we've integrated the rate of change to give me a formula, that an equation that explains what the volume is at any given point. Cool. Now let's have a look at the question and what it's asking for. The question asks me, what's the volume when t is equal to 3? So I'm going to substitute sub t is equal to 3. So what we get is the volume is equal to negative 160 cos 0.5 times 3 plus 1360. Now remember, when I put this into a calculator, this number here is in radians. So just check that in your calculator, that number is in radians. So I'm going to put this into the calculator. Negative 160 times cos 0.5 times 3 plus 1360. And that gives me, to two decimal places, 1348.68 liters, which was what the answer is down here. Great, that worked out. So we have a look. So let's have a look at the steps that we did. So first thing we needed to do was we needed to integrate the formula for the rate of change so that we could get a formula that represented the volume at any given time. Then the question asked me to then sub in t is equal to 3 when the time was equal to 3. And I needed to make sure that the numbers I put into that trig function was in radians. Okay, last part, part 3. We need to find the greatest volume in the pool. We already have the answer at the bottom, if you can see. Now, the greatest, just remember, when we have a trig function, it shows us that the volume here changes over time, and it does this repeated cycle. It goes to a maximum, then it goes to a minimum, and it repeats the cycle over and over again. But with this, so what we can actually do is we can graph our volume function. So here, plus 1360 on a set of axes. So first of all, just remember, we've got this plus 1360. So it sets it up so that my point of equilibrium is 1360. So that's the first thing. Now, a cos function, it looks like this. It starts at a peak, goes down to a minimum, and it goes back up to a peak. Now, for this function, because it's a negative, instead of starting at a peak, it's going to start at a low point, go up to a maximum, back down to a minimum. So I can draw this like this. It starts at a minimum, it reaches 0 at 0 point, at how many, what did I say it was? It reaches a 0 at pi radians. So this is going to be pi radians. It goes to a maximum at 2 pi radians, goes back down to that equilibrium point at 3 pi, goes back down to that low point at 4 pi radians. And it keeps repeating this cycle over and over again. So we know that the maximum is when t is equal to 2 pi. When t is equal to 2 pi, this cos function is just going to be equal to negative 1. So what's going to be? It's going to be v is equal to 160 plus 1360. That gives me 1520, I believe, liters. Another way to think of this is that, just remember, trig functions, the trig functions of sine and cos, they go between the numbers negative 1 and 1. And so what we can think of is we don't even need to think about this cos function that I have here. I just need to think, what conditions make it so that this gives me the biggest number, this whole function here gives me the biggest number possible? Well, let's think of the two extreme points, 1 and negative 1. If this was 1, then I would be subtracting 160 from this number here, which wouldn't give me a maximum. Instead, it was negative 1. This negative 160 would become a positive 160, and it'd give me this, and I'll add it on top of my 1360 here. It should give me the answer that I'm looking for. So that's how you do example 14 on this booklet.